says I'm live. Excellent. For a class of this many people, and only 2 people so far have shown up. I don't know. It's a Monday. I'm still going to teach. I'm still going to do my thing. How many people are in the class? There are 22 active students in this class. 22. And there's 4. I see 4 in the title. Or 4, whatever. I see 4 up. 5. It's going up. All right. Giving people an opportunity to chime in. That's fun. Oh well. So here's the plan. I am going to be introducing to you the last concept of this chapter in polynomials. The plan, which I'm pretty much on pace with the other teachers, the plan was to wrap up this chapter within the next week and a half, give or take. And then we can move forward with whatever the heck we need to move forward with. It's going to be a crazy time. I'm teaching literally to an empty classroom right now, and seeing the number of people actually watching this go from, it was up at 7 at one point, and now it's down to 3. So I'm like, well, that's a good thing, I guess. I don't know. I did say I was going live at 9:30 with a brand new lesson, so that's up to them if they don't want to do that. Anyway, they're going to have to watch it anyway. So in a few moments, I am going to begin what I need to do. Unfortunately, I am in my classroom for this. I would rather be teaching from my desk at home because I have a much better setup for that. If they would allow me to download OBS Studio onto my computer, which I can't because I don't have administrative access to it, but if they would allow me to download OBS Studio, I would actually be able to teach in a much better fashion than what you see right here, and those online wouldn't see that giant glare. Whatever. But that's where we're at. You guys are quarantined, and I'm in the school. And apparently Governor Murphy announced the other day, he said a statewide shutdown is not off the table. It's still an option, of course. And I guess we'll see what happens with all of these wonderful people having Thanksgiving together. Yeah, but I digress. So let me change this just a little bit. There we go. Haha. If you would, ladies and gentlemen, for those of you in attendance today, and I'm going to be checking the chat over when I go sit down because I'm going to have it open on my phone. But if you would, I'm going to need those notebooks out and open. I'm going to be coming back up to the board at various points, maybe, depending on how I feel, depending on if the mood strikes me. But I'm going to be introducing to you, obviously, various important concepts that I deem fit. So let me adjust my window right here so that you can see what is going on. Then I'll flip this over to that. Haha. And now you can see kind of what's going on. Let me get the chat going on over here, because I got the chat open on I'll get the chat open up on my phone so that if you have any questions, of course, I can attempt to answer them as we're moving forward. Let's see. Click. Haha, there I am. I can see the chat now. Excellent. See, I can see the chat right there. See, I'm on my phone right there. There we go. But I got it. It's all good. Okay. Let's zoom out a little bit, make that a little bit more palatable. And let's start with this. Today is 11/30. I'm calling this Intro to Polynomial Graphing. There we go. There are going to be various things that you may be seeing for the first time today. We'll see how that goes. I'm hopefully going to have some things pop up on Desmos at various times. I'm hopefully going to have things pop up on my calculator as well in order to be able to see them better. But we'll kind of deal with that when the time comes. Throughout the course of this chapter, we have been solving polynomials. And in solving these polynomials, we have kind of looked at their graphs a little bit. But today is the first day where we're really going to deep dive this stuff. It's going to be amazing. So let me just kind of, in my calculator right here, let me just kind of throw out a random, I'm just literally typing in, not randomness, but I'm just typing in some kind of polynomial that I can get a visual for. I don't like that one. You can't see what I'm typing. That's okay. As the rain is falling down like crazy. That's perfect. Okay. I'll zoom in on this. There we go. Hopefully the glare won't affect that much. I moved it to the side a little bit. But you can see that polynomial right there. Now that polynomial is not linear. It's not quadratic. It is a third-degree polynomial. This example, you can see in the top left corner of my screen, I tried to show what the equation was. You know what? I'll go to y equals, there's the actual equation. Y equals, it doesn't matter what the equation is, but it's x to the third power. Last week, we talked about the different attributes of polynomials. The degree of the polynomial, determining a lot of different things in terms of the number of turns and the number of x-intercepts that graph could potentially have. Now, this is a third-degree polynomial, which means at most, it could cross the x-axis 3 times. Now, this particular example only crosses once. Only once. No big deal. But it could have crossed up to 3 times. Now, if you count repeats and complex solutions, it does have 3 solutions. It does actually have 2 complex, 2 imaginary solutions, and 1 real one. But that's besides the point. It does have 2 turning points. The 2 turning points in question are perfect. They relate exactly to what the degree is, because if the degree is 3, then at most it could have 2 turning points, n minus 1. These are all from the notes from last week. But today, I am worried about a lot of different aspects of graphing this thing. First and foremost, I want to define for you something called end behavior. End behavior. Now, what I'm doing is I'm actually covering up, or I'm trying to cover up the middle of the graph. And what I would really, there we go. And what I would really like to focus on, and I'm going to walk up to the board for this, is what the ends are doing. And when I say the ends, I'm talking about the left and right ends of the graph. I'm talking about where is it going to the left, where is it going to the right. Those are the quote-unquote end behaviors that I am worried about today. Now, depending on what equation you have, you can determine exactly what the end behavior of the graph is going to be. It's really nice, actually. There's only 4 different types of end behavior, 4 different types. It's where both ends go up, both ends go down. This example where it's like one up, one down in this kind of direction, and then the other one like this. But we'll see those when I actually draw them out. There is a notation that goes along with this end behavior as well. I'm not a huge fan of the notation, but I'm still going to show you the notation because you never know when it's going to pop up, hint, on a major assessment, hint, or a midterm, hint, just saying. So we'll get into all of those details in a few moments. So first, let's talk about the 4 different types of end behavior so that I can show you exactly what is expected of you. End behavior. So the first 2 types. I'll split this like this. Yeah, I'll split it like this. The first type of end behavior that you could have is when both ends are facing up, or going up, to the left and to the right. As I move to the right, the graph is going up forever. As I move to the left, the graph is going up forever. You will have this type of end behavior if you have an even degree. An even degree, a second degree polynomial, a 4th degree polynomial, something along those lines. You will have this kind of end behavior if you have that degree and a leading coefficient that is positive. A leading coefficient that is positive. Excuse me. Now, having a leading coefficient that is positive, the leading coefficient is the coefficient that is attached to the largest degree. So for the example that we have right here, and this is the one that I just had on my calculator earlier, for this example, it is a third degree polynomial, as we stated before, but the coefficient that is with that x cubed is a 1. It's a positive 1. Now, clearly, this end behavior does not match what I just drew because this degree is odd, and this one clearly is even. Now, like I said, there is a notation that kind of goes with the end behavior. I'll share that notation with you in just a moment. Let me talk about the second type of end behavior that you could potentially have, and it's the end behavior where both ends are going down. Now, they're going in the same direction. The same direction. So the degree is still even. The degree is still even. Think about your quadratics. Quadratics tend to either the arms or the ends basically both go up or they both go down. They both go up or they both go down. It's just the way it is. And in this case, that's what these end behaviors are doing. But the leading coefficient determines which one you have. If the leading coefficient is positive, they'll both go up. If the leading coefficient is negative, they'll both go down. Now let's talk about the notation. The notation, again, I'm not a huge fan of the notation, but there's not much I can do about that, simply because these things may show up on some major assessments, like the midterm, something that I don't make by myself. I make it with other teachers, and other teachers like this notation. So that's where we're at. Now, this notation is going to look weird, but I'm going to walk you through it. As x approaches infinity. Now, what that means is as x goes to the right, because on the x-axis, the positive numbers are to the right. As x approaches these larger and larger positive numbers, what is the function doing? What is f of x doing? For this example, as x goes to the right, f of x is going up. F of x is going up. So it's actually also headed towards infinity. Again, that's how you would read that. Now I'm going to read it in the notation, and then I'm going to translate. As x approaches infinity, f of x approaches infinity. What that really means is as x goes to the right, the function goes up. That's how you would translate that. Just so we're all on the same page here. Now that's just the right side. That's just the right side behavior, the right end behavior. As x approaches negative infinity, meaning as it goes to the left, and you can see over here I'm moving to the left, what does the graph do? Well, it still goes up. So f of x would also approach infinity. It's a terrible notation. I know. It is a terrible notation. I am not a huge fan of it, but again, it's something that they will throw at you, and I need you to be ready for it. As x goes to the right, it goes up. As x goes to the left, it goes down. It goes up. That's both of those ends going up. I can do the same thing for this one. As x goes to the right, clearly the graph is going down. So as x approaches positive infinity, the function approaches negative infinity. If I could do a negative sign properly. There we go. As x goes to the right, the function goes down, is the exact same thing as saying as x approaches infinity, f of x approaches negative infinity. The left side's doing the exact same thing. The left side is doing the exact same thing. So as x approaches negative infinity, as x goes to the left, the function is going down. It's just another way of putting it. Again, this notation is not great, but this is the way that they expect it to be written. It's a little weird, I know, but we'll get to it. We'll get it. We'll get it done. We'll wreck it. We'll do well with it. Whatever. All right. Now, like I said, there are 4 types of end behavior. This is just 2 of them. That's just 2 of them. After we go over the 4 types of end behavior, we'll actually be able to deep dive into some of the things about these graphs, which I'm so excited to get to. As I'm in my room, I'm actually kind of freezing because I don't think they bothered to turn the heat on today because they're like, teachers, they don't need heat. I'm legit freezing. My hands are cold. Anyway, back to this. So the other 2 types of end behavior. Split my page again. Here's the 3rd type. The first 2, they both go up, they both go down. Cool. This is the 3rd type of end behavior. Now, clearly, they're going in different directions. The degree is going to be odd. You're talking about your 1st degree, your 3rd degrees, your 5th degrees. Again, the largest exponent is your degree. But if your degree is odd, then you're going to have something that could look like this, as long as your leading coefficient was positive. Now think of your positively sloped lines. A line, a linear equation, is a 1st degree polynomial. And being that it is a 1st degree polynomial, odd degree, could have a positive slope or a negative slope. And in this case, yeah, it would be a positive slope. But if you have a 3rd degree polynomial, like the one that I showed you before right here, a 3rd degree polynomial, I'll zoom in on that, you can see that the end behavior does match exactly what we just wrote down. Zoom back out. The way that I usually distinguish it is, well, if you have an even degree, and this is what I wrote down earlier, if you have an even degree, then your ends are going to be going in the same direction. But if you have an odd degree, wait for it, if you have an odd degree, then your ends are going to be going in opposite directions. I'll pause for applause. I'll say it again just in case. If you have an odd degree, your ends are going to be going in, wait for it, opposite directions. You can't see it right now, but I'm high-fiving everyone in the class. It's really great, actually. Anyway, back to this. As x goes to the right, f of x is going up. And you can see that right there. As x goes to the right, the function goes up. Yeah. As x approaches infinity, f of x also approaches infinity. To the right, up. Cool. You can do the left end behavior. As x goes to the left, the function is going down. With end behavior notation like this, you're basically describing, okay, right and left, where's it going? As you go to the right, is it going up or down? As you go to the left, is it going up or down? There's a little sketch that I can draw, but then I can have the proper notation to describe it. It's fantastic, really. And then finally, the 4th type of end behavior that you could have. Opposite directions again. Opposite directions. Anyway. Your degree clearly is odd. 3rd degree, a 5th degree, a 7th degree. But your leading coefficient here is negative, meaning that the end behaviors form like a negatively sloped line. It's not exactly a slope because you don't know what happens in the middle, but it's kind of nice. As x goes to the right, the function goes down. And as x goes to the left, the function goes up. And that would be the proper end behavior there. I love it so much. It's kind of nice. It's kind of nice. But I digress. Let's look at an actual example. Because writing these things down is one thing, but actually being able to see what's happening is entirely another. So let's deep dive something. I want to draw for you an example graph. And I want you to copy it down as best you can. Now, you don't have to be perfect with this sketch that I'm about to do here. But I want you to be able to see it so that you have the example. So here's just some random XY plane. And I'm going to go, wee, woo, woo, like that. Just some randomness. I don't know what this equation is. I don't care what this equation is. Because I can tell you so much based on what the graph looks like. First of all, look at the end behavior. The end behavior, one's going up, one's going down. The right end is heading up, the left end is heading down. That tells me immediately that my degree is odd. I know that I have an odd degree. I definitely have an odd degree. I can decipher it more. I can tell you what kind of leading coefficient you have. Because it's an odd degree, odd opposite directions, but if you were to imagine a line being drawn from one end to the other, it's a positively sloped line, which means that my leading coefficient, whatever it is a positive number. I'm narrowing it down. I just put in dots for all of the x-intercepts that I can visibly see. It has 5 real solutions. It has 5 real solutions. Now, being that it has 5 real solutions, go back to the definition that I gave you last week. The definition that I gave you last week, okay, whatever the degree is, let's call it n. If the degree is n, then you would have at most n real solutions. At most. At most meaning you could have less. So since we have 5 real solutions, and the degree has to be odd, this means a degree of at least 5. It has to have a degree of at least 5. It could be 5. It could also be 7. It could be 7. If the degree were 7, I would have at most 7 real solutions, meaning this could be a 7th degree polynomial. It can't be a 6. It cannot be a 6th degree. Because of the end behavior, we know the degree has to be odd. Look at the number of turns. Look at the number of turns. The turns fit the information as well. Turns. A turn, to recap from last week, a turning point is a change in vertical direction. Watch. It's going up, then it's going down. There's your turn. Then it's going down, then it's going up. There's a turn. Then it's going up, then it's going down, then it's going down, then it's going up. There's 1, 2, 3, 4 turns. That fits the definition as well. That fits the definition as well. Because the definition was, if the degree is n, then you would have at most, n minus 1 turns. Since it's a fifth degree polynomial, or I'm sorry, fifth degree, since it has 4 turns, that statement about the degree is still true. It still is at least a fifth degree, meaning it could be more. It could be a 7, it could be a 9, it could be an 11. It still fits the definition, which is nice. Let me write out the end behavior. So, end behavior as x goes to the right. Notice what I wrote there. I didn't literally write the word right. I wrote as x approaches infinity. But as x goes to the right, the function goes up. And clearly it does. And as x goes to the left, the function goes down. Which it does. Which is nice. It's nice that it does that. Woo! Excellent. Excellent, excellent, excellent. Okay. I have a big old problem for us to try now. A big old problem. See, because the thing is, everything that we've been doing in the past few weeks is culminating in this problem. The problem I'm about to do with you. It's going to be nice. For me, not for you, for me. Let's see what happens. Here's the problem that I would like to try with you. And our goal, our ultimate goal, is to be able to do as much as we possibly can with this problem. Here's the example. F of x equals x to the fourth plus x to the third minus 7x squared minus x plus 6. I'll repeat that. F of x equals x to the fourth plus x to the third minus 7x squared minus x plus 6. This is what we have. Yes. Now, I can tell you so much about this equation just based on the way the equation is formed. First of all, the degree. The degree is 4. The largest exponent is the degree. It doesn't matter what order it's written in, the degree is 4. What's the leading coefficient? The leading coefficient is the coefficient that is with the largest degree. In this case, it's a 1. So my leading coefficient here is a 1. Make that more obviously a 1. There we go. So what does that tell us? It tells us a lot. First of all, it tells us what our end behavior should look like. The leading coefficient is positive. The degree is even, which means my end behavior should look something like that. Now, that's a sketch. That is actually just a sketch. I am going to write out the end behavior the way it actually should be once we get to the graph. But that's just a sketch. What else does it tell us? Well, because the degree is 4, it has at most 4 real solutions. This is according to the information that I gave you last week. The degree is 4, meaning we could have up to 4 real solutions. Might have less. We don't know yet. We can also have at most 3 turning points. We could have at most 3 turning points. Are we guaranteed to have 3? No. But we could have 3 or less. It really depends. We know what the end behavior looks like. We know how many solutions it could have, how many turning points it could have. So what do you do? Ultimately, we're going to try and graph this thing. But in order to graph this thing, again, like I said, we're going to have to deep dive in. How do we do that? Well, let me flip over to Desmos. Let me flip over to Desmos real quick. Wait. Where are you, dude? Ah, there you are. Hold on. Let's flip over to Desmos. Desmos. Graphing calculator. Let's take a look at this thing. You'll be able to see parts of this. Hopefully, I got the red one here. Equals x to the fourth. Oh, good, it is red. Red is much easier to see. Minus 7x squared minus x plus 6. There we go. You can see parts of it. There we go. You can see most of it. Of course, you could throw this into your graphing calculator as well. It's completely fine, of course. But that's besides the point. I walk up here meandering just because I want to see what this thing looks like. This looks weird down here. Not really sure what's going on. Again, we're about to graph this thing in a little bit. Let's talk about what we know. We know it could have at most 4 zeros, 4 real solutions. And it looks like 1, 2, 3, 4. It looks like we got it. What that means is now we're guaranteed that no other real solutions are going to occur like way off the graph where we can't see them. We know what the end behavior is supposed to look like. The end behavior is supposed to be both going up, and it looks like both are going up. But let's talk about the number of turns. According to the degree, it would have at most 3 turns. And it looks like there's definitely a turn right here. Change in vertical direction. There's definitely a turn up here. And I guess I could surmise that somewhere down here is the 3rd turning point. I don't know exactly where it happens, but that's not the point. We can figure out approximately where it occurs in a little bit. But we know that it should occur somewhere down here. Knowing all of that information just from the equation, knowing the degree, the leading coefficient, the turning points, the zeros, the end behavior, knowing all of that, I have a pretty good idea as to what this thing looks like, but I still have to prove it. And we're going to use the synthetic division factoring skills that we've learned in this chapter in order to prove it. Visually, it looks like 2, 1, -1, and -3. That's what it looks like. But I'm going to prove it. I'm going to prove it using our synthetic division. And once I have proven that I have all 4 zeros, I will have all 4 factors, and then I'd be ready to create a table of values. Let's see what happens. So I'm going to flip my screen back. There we go. And it looked like 2, 1, -1, and -3. It doesn't matter which one we start with. Oh, I can show the last page of the notes right now. Chapow. This one right here? Oh, move that there. There we go. I just threw up the last page of the notes right now. Oh no, message retracted. I don't know what that means now. Was that the last page? Or was that the last page? Now I'm not sure which last page you were referring to. Okay. Not a problem. You know what's really cool about it? Being that this is, I know it's like a live video and stuff. I gotcha. Being that it's a live video, you could pause and rewind it and then go back to live or, just weird stuff. I love YouTube. YouTube is cool like that with live streaming. But let's see what happens now. So I got to test this stuff out. I'm going to my synthetic bar. 1, 1, -7, -1, 6. Those are the numbers. Those are the coefficients that I get from my equation. I know the glare is kind of right there. I do apologize for that. I'm going to test out the first number. Let's test out the 2. It doesn't matter which one you do. I'm going to prove that the zeros that we saw actually work. I'm going to factor this thing completely. It's going to be nice. Synthetic. 1 plus nothing is 1. Multiply, add, multiply, add, multiply, add, multiply, add. Nailed it. Now what we have proven, what we have shown, is that 2 is definitely a 0 of the function. 2 is definitely a 0 of the function. Now again, I'm walking up here to point this out just for emphasis. We have a remainder, constant, x, x squared, x cubed. Now, I'm not going to write down that equation, but I just want to point something out to you. The fact that we have an x cubed equation. We took that x to the fourth, we divided out a factor, and now we have an x cubed. We are whittling down the equation. We are whittling it down to prove not only that the zeros work, but to prove what the factors are going to be. So, I'm going to take that whittled equation, that whittled down equation, and I'm going to do another synthetic bar. Let me separate this, separate that, and I'm going to do another synthetic bar right here with the numbers 1, 3, -1, -3. I don't need to use the remainder. But I'm going to use a different 0 now because I can't use the same 0 unless it actually is repeated, and I don't believe there's repeated zeros here. Well, let's try it with +1. +1 was the next 0 that I visibly saw, because again, when it comes down to this, you visibly check the graph and then divide them out to prove it. 1 plus nothing, multiply, add, multiply, add, multiply, add. Got it. I just proved it. I just proved that 1 is definitely a 0 of the function. Now I'm going to prove what the factors are in a little bit, but let me just point something out here. Remainder, constant, x, x squared. We have a quadratic. Now, when you whittle this thing down to a quadratic, you have options. You absolutely have options. Just as a side note, because of all the rain that's coming down, I really hope that we don't lose power, because the high school tends to lose power when the rain is too much. Just a heads up. Anyway, we have a quadratic. Now, your options when you have a quadratic, you have options to either continue with synthetic division if you wanted to, or once you have that quadratic, you could also use the quad formula or factor it. Let's see what we have. We have a 1x squared plus 4x plus 3. I would like to factor that thing. I would like to factor that thing. I think that would make me happy. Now, if you went through the Tucker method, whatever method you use, it would end up being an x plus 3 and an x plus 1, which, if you solved both of those by setting them equal to 0, if you solve them by setting them equal to 0, you end up with the other 2 zeros that we saw on Desmos. Those are the other 2 zeros that we saw on Desmos. Unbelievable. Now, what have we proven? What have we proven, actually? What we have proven are all of the zeros and all of the factors. Let me actually recap that here. We have proven the following zeros. We have proven x equals 2, 1, -3, and -1. We have proven those zeros of the function. We proved the 2 here, the 1 here, and the negatives down here. You whittle it down. It's wonderful. Absolutely wonderful. We've also proven the factors. The factors, meaning x minus 2, x minus 1, and these 2 down here, x plus 3, x plus 1. We have proven those as well. Now, just for the sake of the visual connection between them, I have lined up the 0 with its factor, the 0 with its factor. You don't always have to do that. I'm just doing that visually for you. The 0 with its factor, the 0 with its factor. You could either express them as zeros or you could express them as factors. It's wonderful, really. Now, we haven't answered the overarching question of this whole thing, which was trying to graph this thing. We need to graph it. And we will in a moment. But we have figured out so much just based on the equation that they gave us. Let me recap what we've done so far. I gave you this equation. I said, hey, we're going to figure out everything about this equation, and then we are eventually going to graph it. Yes, I got the graph from Desmos. I don't care about that. I care about the rest of this stuff. From the equation, you know the degree. From the equation, you know the leading coefficient. Based on that, you know what the end behavior should look like. You know at most how many zeros you should have. You know at most how many turning points this thing should have. We looked at the graph on Desmos and we're able to visibly identify a few zeros of the function, 4 of them actually, to be precise. We proved it. We proved all 4 of those zeros by going through the process of synthetic division and factoring in order to get down to the answer that we were looking for. Now I'm ready to take this a step farther because we have to graph this thing. And when it comes to graphing these types of problems, I am going to be expecting accuracy. I am going to be expecting accuracy. And the type of accuracy that I am referring to is what I am literally about to show you. So just for the sake of argument, I am going to rewrite the equation that we just did. This is the same exact equation. I'm still attempting to graph it. I'm just rewriting it so that I have it on the next page for myself. And here's what you have to do. What I would suggest you do, and you can practice this now for the future, but you're going to need to create a table of values. And the fastest, easiest way to get the table of values is from the graphing calculator. So let me zoom in on this sucker. Here we go. I'm going to check the glare in a moment. Make sure I don't have to move that thing. There we go. Yeah, it's kind of okay. But that's the equation that I'm typing into my graphing calculator. And I'm going to need a table of values. And you can get the table of values directly from the calculator as long as you type it in correctly. The way you do that, and some of you already know this, that's okay. You hit second graph. Second graph will take you to the proper table of values. Now, this table of values tells you a lot. I'm going to copy down some of these numbers. Not all of them. Not all of them. But some of them. Let me scroll up a little. If I scroll up, eventually I get to this right here. This large double-digit number at -4. If you go keep going, it's like, oh, wow, that sucks. But that makes sense. Because as you move to the left, what was the graph doing? It was going up. As you move to the left, the graph went up. As x approached -infinity, the function went to +infinity. That makes sense that these numbers are getting really large. I'm not writing down all those numbers. Instead, I am just going to write down, I'm going to start with -490. I'm not actually going to plot it, but I'm going to write it down. I'm going to write down -490 in a moment. I'll show you what I'm going to copy down. And I'm going to copy down everything that I see after -490. I'm going to copy all of these ordered pairs up to 3, 48. Because
What does the graph do when you move to the right? Well, when you move to the right, it's going to positive infinity, meaning as you go to the right, it's going up. I don't care for all of these giant numbers down here. I am only going to copy down up to 3,48. So let me zoom out and let me show you what I'm going to copy down. I'm going to create a little table of values over here. If I can get the cap off my pen. Little table of values over here. And I'm going to start with -490. And I'm going to copy down literally what I see in the table of values. -3 is 0. -2, -12. -1, 0. 0, 6, which is actually the y-intercept. 1, 0. 2, 0. And 3, 48. I'm literally just copying down the table of values that I saw in the graphing calculator. And I'm going to go as far left and as far right as I need to until I get to numbers that are approaching the end behavior. You need to know what the end behavior is in order to recognize how far on the graph that you are actually going to copy. Now, this actually does make a bit of sense because look at this. X-intercept. -3, x-intercept, -1, x-intercept, +1, x-intercept, +2. Those are the zeros that we found. The y-intercept, it's the y-intercept, whatever, I don't care. But those numbers are going to be incredibly helpful. This is going to be helpful in terms of that extra turning point that we talked about. What do we do with them? Let me show you. As I said, we're deep diving this problem. You're going to create an XY plane, and we are actually going to graph this thing. I got to plot those points. Now, I'm not going to plot -490. No, thank you. But I am going to plot, let's see, -3, 0. Move that over a little. There we go. -2, -12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. -2, -12. There it is. -1, 0. 0, 6. 4, 5, 6. 1, 0. 2, 0. And I'm sorry, I am not going to plot 3, 48. Why in the world would I plot 3, 48? That's ridiculous. Let me show you what we got. Now, these points, you can create the graph from these points. This is not a connect the dots. This is not going to be a connect the dots. I've seen people do this crap in the past, where I've seen people be like, there, I got my graph. No, absolutely not. What the heck are you doing? I've seen people do that. Don't do that. You have to go through the points as a smooth curve, left to right. You have to go through them left to right. When I say left to right, I am referencing their x values. The other thing that you have to keep in mind is this has to be a smooth curve. Has to be a smooth curve. There's not going to be any horizontal lines in this thing. It has to be a smooth curve. And what I mean by that, I mean this. I'm going to start drawing this with that smooth curve like this. And I'm going to try and be as careful as possible because I'm using permanent marker here. But I'm going to create a smooth curve. Now, I stopped right there for a moment because I'm not done yet. I'm not done yet, but I just wanted to show you something. I have seen so many people make this mistake. I've seen so many people create a horizontal line between the two of those. Don't do that. In order to have a smooth curve, this graph has to dip below and then come back up. These are the only two x-intercepts. The only way that that visibly happens is if the graph dips below and then comes back up. Make sure that you are doing that correctly. The other mistake that I've seen people make is I've seen people leave it like this. Do not leave it like this. We spent the entire first portion of this lesson talking about end behavior. Where does the graph go as you move to the right? Where does the graph go as you move to the left? If you're talking about that type of end behavior, then you're talking about the graph doing that and doing that. That is the proper graph. Smooth curve, no horizontal lines, proper end behavior, correct turning points. Remember, we said it would have at most 3 turning points. Here, here, and here. Where's that turning point occur? I don't know. I don't know where that turning point exactly occurs. I mean, if you wanted to, you could, again, do like 1.5 or some junk like that. Or you could look at this and just kind of estimate it approximately where it would be. I'm just estimating it at that point. The accuracy that I am talking about is the end behavior, the x-intercepts, the table of values. That's the details that I'm looking for. Those are the details that I'm looking for. I'm going to be looking for proof of the zeros of the function. I'm going to be looking for the details in the end behavior notation, which I'm still going to have to write in a moment. I'm going to be looking for the proper turning points. I'm going to be looking for all of that stuff. It's going to be amazing. Of course, you do have graphing calculators to help you get most of this stuff, but you have to prove it to me. Yeah. So, end behavior, just to kind of wrap up this problem. As x goes to the right, f of x goes up. That's the right end behavior. And as x goes to the left, f of x is still going up. That is the left end behavior. It's amazing, really. It's amazing. I love it so much. Now, this is just your intro to this stuff. It's a culmination of a lot of information. Last week's information that we've been doing throughout this entire chapter with synthetic zeros, tables of values, all that wonderful stuff. Now end behavior and graphing. This information will come back in a big way, but we will revisit it on Wednesday. So, between now and then, keep an eye on Google Classroom just in case I throw something at you. Eventually, we are aiming for a major assessment on this information, on this entire chapter, that is, really. The minor assessment on Edge Elastic that you guys did for me, which was due last Wednesday, not everyone did it. I have gone through the scores, though. I have updated them. There was one question where you had to describe how you would do something, and I had to score it by hand manually, and I did, and I updated those scores. So you can check Genesis, and if you have any questions, you can get back to me. Oh, yes, Joe, it's always just the beginning. It's always just the beginning. Anyway. All right. If you have any questions, of course, you can contact me. Like I said, pay attention to Google Classroom. Otherwise, you do have a few minutes left, so I am going to end the stream literally just 2 minutes early or some junk like that. I don't know. I don't care. But yeah. Hope you have a wonderful rainy day where you're stuck inside. Whatever. I'm stuck at work with nobody in a cold room. So feel bad for me. Whatever. Anyway, everyone have a wonderful day. Make sure you take everything from under your desks and make sure you don't leave anything here. And have fun in the hallways. All right. Goodbye. Bye-bye. Bye-bye. Bye-bye.